Hello everyone, welcome. Our poster is titled Perceived Numerosity in Crowded and Uncrowded Displays. Humans have excellent abilities to process non-symbolic numbers. When presented with small numbers of items, usually up to 4, we can enumerate their number accurately and rapidly. This is called subitizing. The performance of enumerating higher numbers of items is much worse compared to subitizing. And this is numerosity estimation. What are the factors that affect numerosity perception, especially the perception of a large number of items, so that we become imprecise? One of the proposed factors is crowding. Crowding refers to the inability to identify a target when it's surrounded by neighboring flankers. On this display, a target T is surrounded by two flankers F. When fixating the cross, the identification of the target T is quite difficult when the target and flankers are close to each other. There is a certain region around the target in which flankers interfere with target perception. If the flankers are placed outside the region, they stop interfering. This region is called the crowding zone, indicated with the ellipse. The size of the crowding zone increases with eccentricity, that is, the distance of the target from fixation. Importantly, if flankers are placed in tangential directions, flankers stop interfering with target perception with a smaller target flanker spacing compared to when flankers are placed radially. This is a key characteristic of crowding named radiotangential anisotropy. In this study, we aim to investigate the role of crowding in numerosity perception. In order to test a crowding-specific role, we presented both crowded and uncrowded displays to participants. Now I will show how we generated the crowded and uncrowded displays. On this display, you see a disk with its estimated crowding zone. Now an extra disk is added inside the crowding zone. We refer to such a condition as crowded. Let's call the central disk base disk and the other one extra disk. Now we place the extra disk outside the crowding zone, but at the same distance to the base disk. According to the radiotangential anisotropy of crowding, the extra disk that is placed tangentially to the base disk, as we see now, should interfere with the base disk less than when the extra disk were placed radially inside the crowding zone. Therefore, we refer to a condition like this as uncrowded condition. Here we demonstrate the actual constructions of displays. Red ellipses represent crowding zones of the corresponding base disks. In crowded displays, each extra disk was added inside the crowding zone of the base disks. For uncrowded displays, extra disks were tangentially added outside the crowding regions. We ensured that the average spacing between base and extra disks were the same in crowded and uncrowded displays. In this way, we generated displays that are different in crowding levels while keeping other physical properties between the two conditions the same. Additionally, we varied the number of extra disks per base disk to control the influence of clustering of disks in the displays. In each trial, the display was presented for 150 milliseconds, and participants were required to type their best estimate. We tested two numerosity ranges in the experiment. And here are the results. The y-axis shows the deviation score. It is calculated by subtracting the actual numerosity from participants' response, so that deviation scores above 0 mean overestimation and below 0 mean underestimation. The two numerosity ranges we tested are shown on the x-axis. Crowded and uncrowded conditions are shown in red and green respectively. In the small numerosity range, there was no difference between the crowded and the uncrowded condition. However, in the large numerosity range, deviation scores in the crowded condition were smaller than in the uncrowded condition, showing that crowding modulated numerosity perception. To conclude, in the current study, we used the radiotangential anisotropy of crowding to create displays with different crowding levels while controlling other possibly confounding factors between the displays. Overall, our results show that crowding decreased the perceived number of disks compared to no crowding when the numerosity was large, indicating that crowding does play a role when estimating large numerosities. Thanks for watching.